Greetings. In this one, we will delve into the field of graph theory, which is a mathematical field in which we take care of graphs, so-called graphs, which are basically mathematical objects. I'm not going to go that deep into the definition. We're doing a sort of more surface level video regarding this, but generally the way that we will need to understand it in order to be able to work with it, and I mean by it, I mean graphs, a graph. A graph is basically a structure consisting of vertices, points, and edges that connect these vertices. So you can imagine it as a set, and then those points, individual points in that set, are either related one-to-one by an edge, connected by an edge, or they are not connected to each other. So if there is an edge between two vertices of a graph, that means that these two vertices are so-called neighbors. And I can just draw an example of a graph for first. So let's say we have a graph of 3 vertices, so these are such points. And let's say that all of them are mutually connected. By the way, this is concretely going to be the graph K sub 3, which means the complete graph of 3 vertices. And I haven't described exactly what that means and why that is so, but let's just see this example, and I'm going to explain this in a second in actual context. So if we have this graph, it has 3 vertices, that's given by this 3, by the way. I'm going to make it more concretely understandable in a second, as I said. So this is a graph, the points, the endpoints are vertices, and what connects them are edges. And now, either the points can be connected by an edge, or the edge can be not there. And if it's not there, then there is no such edge. And so each graph is going to be given by 2 parameters, namely V and E. And if I want to be more concrete, when we're working with more graphs at the same time, we also want to mention which graph we're talking about the V of and the E of. And the V and E are the number of vertices and number of edges in that graph. So, I mean, it's not necessarily the number, it's rather the set. If I want to talk about the number of vertices and number of edges to be more concrete, I will talk about the magnitude of these sets. So, by the way, if I also want to make it very clear that I'm talking about the vertices of G by this V, so I'm defining a graph G. Let's go back a second to make it very clear. I'm now talking about or defining a graph G that has the set V of its vertices and set E of its edges, where vertices are the points as we see intuitively here, and edges are those possible lines that connect them. And I can also call these vertices something. So very commonly we can call them using numbers. So we can have them named. And okay, let me just put this edge back there. And then we can either say, so for example, we have V and E, and as I said, this is vertices, this is edges. So if I'm going to talk about vertices, then I'm going to write this as a set. I'm going to list the vertices we have. So for this exact graph, we have vertices 1, 2, and 3. And edges, well, let's list the edges that we have. Those are the connections between the vertices that we possibly see here. Well, I see 1, 3, 3, 2, 1, 2. So 1, 2, 1, 3, and 3, 2. So these 3 edges we have. And now we have listed all the edges that we have and all the vertices. But if, for example, I had deleted the 1, 3 and left it that way, and I didn't draw it back, we wouldn't have the edge 1, 3. So it's possible not to have some edges. But the idea of a complete graph, and this is already a concrete example, we can have a graph like this, for example. It doesn't have to be like a cycle that connects in a cycle, that it starts and you can go along the individual vertices across the edges between the vertices and then come back to the same vertex as we started at. That doesn't have to happen. We can also have such a graph of 2 vertices, and then of course, how can you have it cyclical? And now I'm not going to go into the details of how you can draw it. You don't have to draw the line straight. You can also make them bend or something. There's a lot of context to consider. But in this one, we won't really go deep into this because it will take a lot of concrete talk. We will rather focus now on some concrete example. That's a little bit more interesting in the context of directly applying the idea of a graph. So just to quickly reiterate what I was going to say is, we are talking generally about a graph, and the most general name is G for a graph. It's defined by its set of vertices and set of edges. And the point I almost made and I didn't complete it, but here I'm gonna make it. If we put in the parentheses this G, it basically makes it more clear for us that it's the vertices of G and the edges of G on this graph G. We could also have another graph H, and then again we would talk about V and E, but this would be V of H and E of H. So just to make it specific, just to make it explicitly mention that these do have this parameter of what they are actually connected to. So if we're talking about the set V, well, we should also specify we're talking about the vertices V of H or of G in case of G, and so on. So that's what we're doing. But now let's say this is G, and let's say that this G is this K3 in this case. Let's just say that, right? This is already a methodical or like a technical name for this concrete graph. For this concrete graph of three vertices which are all connected. And I'm going to go back to what I mentioned in the beginning. It's a so-called complete graph. So we've gotten a quick intuition for what the graph can look like, what it can seem like, what it can be. But a complete graph is a special type of graph. We can have graphs where not everything is connected. And I can better illustrate this if we took an example of, and let's draw it quickly, if we took an example of some more points, and let's say not points, vertices, let's say call it the right name. Vertices, let's say we have 4, and then we have them connected by this. But you see that again, if we wanted to have the same, and let's again make them these round empty circles, which we can call them by numbers. So 1, 2, 3, 4, that's going to be their names. And now we have edges, we have vertices. The vertices are namely 1, 2, 3, 4. 1, 2, 3, 4. And the edges, and I'm not calling this graph anything, I'm just talking about V and E because that's what is related to this one. I didn't name it, so I'm just typing V and E, right? The set of vertices, the endpoints, and the set of the lines that connect the individual waypoints. Again, called after the endpoints that the edges are concerned with. So this is edge 1, 4 because it connects vertices 1 and 4, right? But we don't have all the possible vertices combinations connected. We miss this one, we miss this one. So this is not a complete graph. So let's go back a bit and recall back. So a complete graph is something like a graph like we have here. A graph, we just take a plane, draw vertices, and do edges, but we must have an edge between any two vertices of that graph. If it's not satisfied, then it's not a complete graph. So a complete graph is very nicely defined this way. A complete graph, you have some vertices, some n number of vertices. In this case, we have 3. So it's k sub 3, that's the naming. Complete, k is the notation here. K sub the amount of vertices of that graph. And it's complete if all the individual vertices are connected by edges. And here they are. It's a free vertex graph. And it basically is a triangle. It's also quite a methodical name that's used here. A triangle is basically a K3, a complete graph of magnitude 3, meaning it has 3 vertices. So if it has 3 vertices, the way we can have 3 vertices like this and have all connected to each other is by having them as a triangle. It's also a piece of this whole terminology here, that we are calling two vertices adjacent if they're connected by an edge, and if you have two different vertices adjacent to the same third vertex, then they are forming a triangle. And that can be part of a bigger graph. So we can have a graph of more vertices, but if we can identify this in it, then it's a triangle inside that graph. So nice, with that, we've talked about this. And let's now take a quick dive into something related to so-called Ramsey theory, which is very interesting. Ramsey theory deals with and of course that's a wide theory. So what we will consider here is we'll just take a concrete example with Ramsey theory, and very roughly what we can say as one of the main points that we can spot within Ramsey theory. If we want to really simplify everything, I would say Ramsey theory helps us find the minimum number of, especially think so-called Ramsey number, is basically the minimum number of vertices that our graph has to have when we want to find some subgraphs inside that, some complete subgraphs inside that graph with some particular properties. But more generally, when we're looking for some properties of some substructures in a graph, then we want to see how big that graph has to be in order for these substructures to be guaranteed to be present. So let's quickly just say what a subgraph is. Just like we have a set and subset, I definitely recommend to know this first. When you have a subset and a set, basically a set contains everything that the subset contains plus possibly something more. So if we have a set ABC, then AB is a subset of ABC, right? And ABC as a whole is also a subset of itself, but that's a trivial case and we're not considering that necessarily, although in graphs and subgraphs it's exactly the same. We're just talking about the graph, and then let's say we just pick these 3 vertices, and that's a subgraph of just these 3 ones. And we also must have the edges to be also a subset of the edge set of the graph that it's the subgraph of. So we cannot have an extra edge suddenly there. Okay, so this thing, when we just take these 1, 1, 4, 3, 1, 4, 3, that's a subgraph of this 1, 1, 1, 4, 3, 2, 1, 1, 2, 3, 4, right? Just took it from this side, so it reverse counting, but you get the point. But if I added this edge, no longer a subgraph because it has something added that this one didn't have. It must have less, but must have no replacement nor addition in place of what was removed. So this is a subgraph of this one, all right? And now, we will talk about this Ramsey theory that I already kind of almost dived into a second ago, but we didn't develop it yet. And Ramsey theory deals with complete graphs. I've already explained what a complete graph is roughly. We've shown an example. And we're really on the surface, but let's just look at an example and see if it makes sense. Ramsey theory generally, as I said, deals with finding Ramsey number, concretely, a minimum number of vertices a graph has to have in order to guarantee some substructure property. And let's say that we will talk about the Ramsey number, and that is related to a complete graph. So let's say we have a complete graph, and let's say that I will take, and this is one of the most common examples one takes as first when one dives into this, a complete graph of six vertices. So K6. So if I have a complete graph of 6 vertices, I will draw it. Again, okay, the naming like before. So 1, 2, 3, 4, 5, 6. Alright, so let's connect them all. And a complete graph, as I said, all the vertices have to be connected to each other. We will have a lot of connections. So we have to make sure that this one is connected, this one is connected like this one is already taken care of, this one. Then we have this one, we have to connect this one with this one. Then we have to connect this one with this one, this one with this one, we have this one. And then we go back, we have this one, this one, this one, this one, this one, this one, this one. We don't have this connection, but we have this connection. Then we have this connection, this connection, this connection, this connection. Let's just check everything. We have this one, this one, this one. I think we have all the edges. So we have to have edges between any 2 vertices of this 6 vertex graph, all right? So the amount of vertices of this one, so of K6, let's just call it the general name, right, is 6, because that's the definition of the naming here. If we have a complex complete graph sub 6 with an index sub 6 here, then index of 6 here, then it has this magnitude of vertices of 6. So that's that. And we have this complete graph. I drew it with all the edges, right? And I drew it as this cyclical thing. And this is probably the most common way one would draw it. Picture looking almost like this. And now, let's dive into a bit of using Ramsey theory for this. So the Ramsey number, what it talks about, is the minimum number of vertices that our graph has to have if we take the graph, then a complete graph of those vertices. So let's say we're looking for a complete graph, and then we know a complete graph, it must have a lot of edges, right? It has a lot of edges because it has to have connection between all the possible vertices. And now, depending on the number of vertices, we can directly then calculate the number of edges. There's direct formula for it. For complete graphs, you have a formula, you just plug in, and within a few seconds you have the number of edges that you can expect. But we're now just talking about the vertices, which is in this case, of course, lower than the number of edges. They're far more edges than vertices in this one, as one can visibly see. And that goes wilder and wilder with the rising amount of vertices that a complete graph could have. Higher complete graphs with more vertices. With complete graphs with a higher number of vertices, yes. So, the Ramsey number will talk to us or let us know how many vertices we need to have for a certain thing to arise. And I've talked about subgraphs, and there's one thing that we should introduce. And namely, it might be a little bit complicated because generally this is introduced in the context of coloring the individual edges we have in our graph. So if we have edges like this, then we can ask Ramsey theory some question. We can, for example, request that we can first of all take all the edges we have in this graph and then arbitrarily color them and ask Ramsey theory how many vertices in the first place such a graph must be. All right, so what level of complete graph it must be for us to be able to find subgraphs that are also complete within those randomly colored edges. So if I have these several edges inside a graph, and I decide to randomly color, let's say, usually we refer to, for example, blue and red. So let me color any vertices that I want by blue and the remaining ones by red, or any ones I first choose by red and the remaining ones by blue. So I color some of the vertices by blue, some of the vertices by red. I want the minimal number of vertices, I'm talking about edges. Some of the edges by red, some of the edges by blue, how many I want by each. Just I make sure everything is colored by either color. And then I'm asking, what is the minimum number of vertices we want this complete graph, this whole one, this K6 in this case, to have? So this one has 6, we see, right? What is the minimal number of vertices we want such a graph to have in order to guarantee us that in this number we have a complete graph of this magnitude? That's a subgraph of this graph that for which we're looking for the minimum number of vertices we'll have as a complete graph, and for this other color for these vertices of this other color to contain a subgraph for this in this case K6 to have another subgraph that is also a complete graph. So let's see about that. Generally, a Ramsey number will be named like this: R of M and N. And what we are talking about here is basically we want to find a complete graph. Let's say we are not in this case, we want to look for a graph, and this is also, by the way, a thing I mentioned, a simple graph, and there are also other types of graphs, but we're not at all looking at these in this case, because we're just referring to graphs as I've introduced them. All the information I've said about graph is sufficient in order to understand this point. So we're not talking about other cases or other viewpoints. Anyway, this is a so-called Ramsey number, is defined by two parameters, and the two parameters say this: we want to find, it's going to be equal to usually n, and the n will be some magnitude of the number of vertices of a graph we're looking for. So how many vertices does our graph have to have in order for m and n to be satisfied? And now I'm going to describe what m and n are. So that's the important part. Let's say that I decide to color some vertices by red, and I don't even know what graph it will be at because I don't know how many vertices it has. That's why it might be harder to imagine. But let's say that I know already for K6, I can find if I color by two colors, I can find a subgraph that is a triangle, a K3, a three vertex subgraph within one of the colors. So I can just look at one of the colors, and inside that color, I can find a subgraph that all the edges inside that subgraph will be with the same color. So if I randomly color some things by red, some things by blue, I'm guaranteed that I will get a subgraph, and not only will I get a subgraph that's a complete one, a triangle, namely, but I will get one where all the three edges of it are the same color, even though I colored all the edges inside, for example, this K6 randomly. So let me go back and kind of switch direction for a bit. And let's say that I just look at this graph. I know it's complete graph, K6. And I say I don't have two colors now. So I'm just going to make the edges that are red thicker, and thinner are the ones that are supposed to be blue. So let's say this one is red, right? I say this one is randomly red. I just choose any number, but I leave some edges to be blue, right? I'm not even counting how many I made red. The thick ones, the ones I made thick, are supposed to represent the red ones and the other color, whatever the colors are chosen to be, right? And now I know, by Ramsey number, I know that if I want to look for complete graphs of magnitude 3, of 3 vertices, to be subgraphs of my graph, I need the minimum number of vertices I need for a graph to have such subgraphs is 6. So basically, why I draw this K6 is already basically predetermined and expected already in advance. And there's a reason why it was chosen. Because we know that the Ramsey number of parameters 3 and 3 is equal to 6. And at this point, I think it's more practical to more generally again refer back to the general notion of a Ramsey number. And because we have M and N, I will just call this other side A, because we would have an N again. I don't want to make it confusing. It was a little confusing here perhaps. The N was not the same N as all on the right side, so we are going to use a different letter. Just imagine there had been an A here, not an N, because we will have an N on both sides. That would be bad. So we have R of Mn equals A, and A is, and let's just say on the other side, it's directly the magnitude of the set of vertices of the graph. R of M and N is the minimal number of vertices our graph has to have, Kn or K magnitude V of G of that graph, such that we can have when we randomly color the edges of that graph afterwards, no matter how many edges we color with one color and then the rest with the other color, we will have a complete subgraph inside it with only one of the colored edges among only edges colored by color 1 with M vertices, and another complete subgraph or a complete subgraph of N vertices within that other colored within those other colored edges, which is very interesting. And namely, this is already a solved result. There's not a direct formula for all possible combinations yet. There's a lot of uncalculated results yet. Still, till this day, we still have a lot of combinations. Here we have 3, we know that's 6. We know that if we want to see that there's a complete subgraph of 3 vertices in one color among one of the colored edges, only if we look at one of the only at the edges that were arbitrarily colored by one of the colors, we can find within them 3 vertex subgraph, and then we can also find a 3 vertex subgraph within the rest of the edges colored by the other color. Then we need a minimal amount of 6 vertices for that graph, which will have these such subgraphs after the coloring. But for some other combinations, let's say we want 4 and 6, there's going to be a different result. And for a lot of even not that high numbers of these two parameters, the Ramsey number, which is the result of this right side is 6 in this case, which will result into this K6 that I drew here before introducing the Ramsey theory, Ramsey number here. For a lot of values, it's not yet known. So that's a big point. All right. So that's what we're talking about. And also, if we want to be very concrete in this case, within Ramsey numbers, or trying to understand Ramsey numbers, perhaps even a nicer way to first view it and to first look at it is not to look at Ramsey theory in general, Ramsey numbers in general, but it's nice to just consider the case of K6. So we could ignore all the stuff that was said around it and just look at K6. And we have K6, again, complete graph, 6 vertices, all connected by edges. So we have some amount of edges depending directly on the vertices. For complete graphs, as I said, we have direct algebraic simple arithmetic formula, which will result in us being able to quickly calculate the amount of edges depending on the known amount of vertices, which is lower, of course. So case 6, we draw it. We draw all the edges between all the possible vertices, any two different vertices. And then we take two colors. I don't have the colors, but I just made some vertices thick and the others I left thinner. That's my other way of distinguishing them. You can do colors, you can do this. And then within those, I know I'm able to find a subgraph of magnitude 3 because I have a K6. Because I know that the Ramsey number for 3 is 6. All right? And of course, we could try to find it. Is it really so? Well, let's look at now. I mean, it might seem a little bit obvious because there are so many edges. How could it be so that we would not find a subgraph that's a triangle? We need K3, a triangle, right? A triangle, I'm always referring to K3, complete graph of 3 vertices. Well, for example, 1, 3, 2 is a triangle, a subgraph, complete subgraph K3 of this K6. That's all within the thick lines. Let's look at the thinner lines. Well, can we find some? Well, we have this one, 3, 5, 4. So yes, we found for both colors, in this case we have the different way of distinguishing it, we found complete subgraph. So this is a small example regarding Ramsey theory, and to quickly go back to what we've talked about today here is basically a quick introduction to what it means when one is confronted with a graph, what a graph can be seen as, how a graph can be understood. We have vertices, we have edges connecting them. Each graph is defined by a set of vertices and a set of edges. Some edges can be left out, but we mostly, for the most part in this one, talked about complete graphs, which are very significantly studied, and they're important because they have the specific property of having any two different vertices connected by an edge.